So today we'll continue whatever we have mentioned in the previous time, and we will concentrate more on something called R format or register format. So what is the register format? This means that the 32 bits that I have, it has a certain format in order to direct the instruction. And any instruction that will use this R format has to follow that particular format given here. So just again, you can think of this as a 32 bits format. And we would like to use this 32 bits format. So all of us, if we would like to write an instruction, will be in the same exact shape. So it will be as a standard for us and also for the computer. So when we design the computer, either in an FPGA or like in the software side, it will follow exactly that particular format. Let's dive in this format and understand each of the format items and what does it mean and why it has all of these kind of bits. First of all, if you have any instructions, let's say you would like to add, as you can see here, I have to include something that basically will say that I would like to add not and, not or, not any other thing else. I would like to have an add. So logically, I have to have some bits inside my format to indicate that I would like to do an addition, not anything else. And that's why we have these two parts here to indicate that this is an add format. So I have here 6 bits, and I have here another 6 bits to indicate that this is an R format and this is an add. How? There is a table that I have to follow. You don't have to remember, of course, the numbers in the tables. It will be given to you. You don't need to remember that, but you need to know where to get it or how to get it. So the add format, when you go to the add, it will tell you that it has a certain opcode and a certain function, means number. So here, let's say we'll have 0. Let's say here we'll have whatever X number, 13, 14, 15, depending on the number that is associated with the add, which will be given to you. And this will be common for all the maps that we are following throughout the semester, and any maps also that you will find outside the class. And this does make sense because I would like the computer, as soon as we'll see some bits in that 32 bits, from that particular bits, I will understand as a computer that this is an AND operation. Correct? Now we begin to step by step understand how the computer will understand what we call the machine language, which is just zeros and ones. If you think about that, if this is 0 written in 6 bits, so it will be all zeros. If this is whatever the number is, it will be again written in zeros and ones. Correct? And the computer understands from these zeros and ones combination that this is actually an addition. So it will direct, as we will see later, the arithmetic logic unit, which will be like a hardware part, to do an addition for the particular input that is coming to you. Then I have also to tell the computer other stuff. And also we have to follow a certain particular template or rule to understand what else I need to do. So it is an addition, but add what to what and where I should allocate the results. Correct? For instance, this might be like something that we need to understand. And that's why has been created in that R format places where it will direct me to know this particular information. what exactly I need to add, and where I should allocate the results. And that's why we have something called here RS, which refer to the first source, 5 bits, RT, which refer to at the second source, again 5 bits, RD, which refer to the destination address, which is RD. So again, this here, first source, second source, and this destination address. Please keep in mind that this is address, and also this is address. What does it mean, an address? Meaning that is not giving you the value, but it's giving you where is that value. Assuming that here, since we have the register, if you recall from the previous time, the register is just 32 registers. The whole register is just a small 32 registers. And in each of these registers, I have 32 bits. I have 32 bits in each of these drawer, if you will. So I have a big drawer. In this big drawer, I just have a small 32 drawers. In each of the 32, each of these drawers, I have 32 balls. If you think of this just like in the implementation side, as an example. So I'm telling you, please go. You would like to add 2 things. The first thing that you need to add, go and open drawer 2. So I'm giving you the address. I didn't tell you when you will open drawer 2 what you will find. I just told you go to drawer 2. And here will be the address that I'm referring to. There is an address will be written here. 2 in that sense or in that example. I have to tell you also where is the other number to add, where it is located. I might say go to drawer number 5. So I will write here 5 for instance, and here 2. Again, this is address. Go to drawer number 5. When you will open drawer number 5, you will find that number. Whatever that number is, it doesn't matter for me right now. I just would like you to add whatever in drawer number 2 with drawer number 5. Write the result as an example in drawer number 7. Just remove the word drawer and write register number. Register number 2, register number 5, register number 7. So I give you all of the information. And since I'm talking to the CPU, so the CPU will just decode the number that is here, will understand what that number is, and then we'll go to that particular register and just take out all of the balls that is inside and count. Or see whatever the number that is there in that particular small register and read that number, and then we'll take it to the ALU. We'll do the same with the second source. And then after I will do the addition or whatever I have here, and or whatever the multiply, whatever the operation that I have here, I will put the results where I will look here. If here is written 7, I will go and open drawer number 7 and just dump the results there or feed the results there. This is exactly what I need to do. Correct? But interestingly, we have some of the command that is not doing addition or and or stuff like that. It's not taking 2 inputs and then get a result of an 1 out. There's some other commands that is basically just shifting. So I'm taking just 1 input, do a little bit of shifting, and then after the shifting results, then I will have an out. So in that sense, I just need 1 input. Yes, let's say like the first source. I will shift it by a certain particular number of bits, and then the output will be again in my destination register. But also with the same idea that I'm not talking about the numbers, I'm talking about the address. So I will give you the address of the register that you need to go and look at that number. I will tell you by how many amounts you need to shift, and also shift right or shift left. And then put the output in the destination register. But take into consideration that for the CPU to understand that this is shift, it has to look at that particular place, which means it will look at that and it will look at that. And from the tables, it will understand that this is a shift operation. And that means I don't have to look at all of the others as I have done with the addition or ANDs or ORs or whatever the other operation is. Okay, so since we have mentioned like all of these, just like again, this is just shift amount. After we mentioned like each of these items, what's exactly meant, we need to dive in a little bit on understanding why we have to choose each of these with this particular number of bits. Or if you were to be a designer, how you would design such a format, for instance. Because you might be asked in the future with totally different format or totally different number of bits, and then we'll ask you to make the design. You will be a design for something else. It's not MIPS for something else, or MIPS for with 64 bits, as an example. How you would think about it. Remember again that the problem here that we have a register. This register is basically 32 bits is the width, and it is 32 different registers. And I would like the CPU to know how I can address any of these registers, or if I would like to shift, how much I shift in total of these 32 bits. So if you were to think about the number of bits needed for each of these instructions, how you would think about it? So the answer that we need actually here 5 bits, because basically, if you recall, we have 32 of these, and I need 5 bits to address any of these. As we mentioned, if suppose that you have 3 locations, and I'm asking you how many bits do you need to address this location, if I'm giving you only 1 bit, let's say 0 or 1, will not be enough, because this will be 0, this will be 1. How about that? That's why at least I need 2 bits. So this will be 0, 0 as an example. The other one will be 0, 1, and maybe this 1, 0, and the 1, 1 will not use it. Or if we have a fourth one, then I can use the 1, 1, and so on and so forth. Here I have 32 of these. So 5 bits basically will be enough to address any of the 32 locations. But this also will be needed for the first source. It will be needed for the second source, and it will be needed for the destination, because all of them can be any of these 32 registers. So I need 5 bits to let me know that please go to register number 1, add it to register number 4, put the results in register number 31st or so. And that's why I need all of these 5 bits. Okay, so now we understood why we need 15 bits now out of the 32. We still also the shift amount. How we can do the shift amount, or why the shift amount here is 5 bits. With the same analogy, but instead of the third vertical axis, in the horizontal axis, in one register, I have actually 32 bits. So if you were to shift, the maximum that you were to shift is from the far left to the far right. How many bits? Again, 32. Correct? How many shifts? Sorry, 32 shifts. Correct? How many bits do you need to account for a shift of 32? Again, 5 bits. So I can tell you, please do this number of shifts. So the maximum will be 32, and that's why you need at least 5 bits. Does this number, could it change? If the problem that you are trying to solve change it? Yes. Suppose that you have 64 registers, different registers. These are 64. Those 5 bits will be enough? Of course not. You need to think about what would be the minimum number. If this here 64, but this is 32, this will be enough as a shift amount? Yes, because this is 32. How about if this is 64? Is 5 bits will be enough? Not, and so on. So then we can play with all of these kind of things. However, if you do understand the concept, then you will not fall in the trap. Okay, so I have now already knew why I have shift amount of 5 bits and why this is 5, why this is 5, and why this is 5, and why I need all of these. Then the rest, I can just use it for identifying what is the function. It's as simple as that. Just the rest I have used to specify what's exactly the function. And the MIPS researcher at that time, they choose to just to separate this for two stuff. One, the very first one that will be common with all of the other format that we will explain in the future, the very first 6, which might identify which format. So as soon as I will look at the operand, I will know the format, R format, J format, I format, any other format that I may have in the future. They have decided that. And then the very last 6, they will call that this will be for the R format as a function, meaning I could have 2 to the power of 6 different options of different instructions, add, addition, and multiplication, blah, 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 and all of these kind of things. And of course, with this 6 and 6, there is still like a lot of options or number that I haven't been used yet, but it will be helpful in the future in that regard, if we suppose that we will need more instruction types, for example. So after we have mentioned all of these things, let's take that example. So I have an add T0, comma S1, comma S2. What does that mean? Meaning that I will add this plus this, and then put the results here. What is T0? What is S1? What is S2? All of these are referring to a certain particular numbers inside the register. You don't have to remember that. You will go to another table and say like, oh, S1. What does it mean, S1? S1 in that table will tell you that this is register, for instance, number 17. What is S1? It is 16. What is S2? 17. What is T0? 8. As an example, this is just like whatever is written in the table, you will just follow. Which means, by another sense, please go to register number whatever, take whatever is there, plus, or sorry, yes, add, plus whatever in register S2, which whatever the number is, do the addition in the ALU, and then put the results in T0, which when you will open, you will find maybe that this is register number 6 and stuff, or 8, or whatever the number is. So if we were to write that into the R format, you will go to the table and see what does an addition mean in terms of the operand and the function, blindly. I mean, you don't need to think about it, it's just in the table. You will find that in the table, the addition holds operand 0 because it's an R format, or all R format for your reference will have a 0 operand. And what is the function number? It is 32. Okay, so you will write here 0, you will write here 32. Then the first source, it is S1. If you go to that table, you find S1, it is 17. So register number 17. So you will write here 17. Go to register number S2. You will see in the table that this is register number 18. Go to register T0. You will see in the table that this is register number 8. So you write all of these numbers. 0, 17, 18, 8, 0, 32. Just write that in binary. So now we have the whole 32 bits in binary like that. So this will be the whole number. If you transfer to hex, this will be the hex. Number 4, that. So you as a human being, when you will see this, you will understand that I would like to add this with this, put the results here. The CPU will see this and will understand exactly the same thing that you have already written, or that we have already agreed to, which is called the machine language, which is just the zeros and ones. So now we get the relation. What is that meant with the machine language, and how the CPU basically understand this kind of zeros and ones. So again, here is the register. We have here 32 bits. The output of this register will be the first source. The second output will be the second source. So you can think of this as a pipe that will take out whatever is in the drawer with a certain particular number. So I will tell you first, with the 5 bits, what is the address of the first source, or what is the address of the first drawer. Suppose my address of the first drawer is here. Let's say 5th. As soon as I will say 5th, a valve here will open. All of these will be thrown outside through that particular output. And that's why that output has 32 instead of 5, because the output will be 32 bits. The same would occur with the second address. I'm telling you with 5 bits where it is the location. As soon as I'm telling you that this is the location, a valve will open, and then it will take all of the outputs to my second source. Then after that, I will have an ALU here. The ALU will take this, and will understand, let's say I would like to do an addition. Okay, so now the addition is ready. Where I should allocate that? This guy is connected here. It's connected. That's why it is connected with 32 bits. Because it is an addition. Addition of this plus this, I still have, let's say, 32 bits. Where I should dump these 32 bits? Which one of these? This guy will tell me which one. Let's suppose that this is here. A valve will be open here, and then all of these will be dumped inside that particular location. So here you can think we have two read ports, one write ports. As we mentioned, also we can have even 64 word file. Might be a little bit, of course, slower than a 32-bit, because now I'll take more time to read or to write. So here, just for your reference, with a shift left in MIPS, it will be written like that. Shift left logic, shift right. Of course, in C or Java, it will be like that, but in MIPS, the assembly, it will be shift right logical. Bitwise AND, in C and Java, it is like that, but in our case, it is AND and I, and we'll understand later on what does it mean here, this I. The same with OR. This is in C and Java, but in MIPS, it will be OR and OR I, and as I mentioned, we'll explain later what is that I. Not, then in MIPS will be NOR. This is the syntax, just of the language. I am expecting, of course, that you will be familiar and we will remember the syntax of the MIPS operations. Most probably, we'll just go with the things that we cover either in class or in the labs. But anyway, try to be familiar with the MIPS syntax. Let's take an example of the shift operation. But just we would like to highlight an important things regarding the shift operation. If I were to shift left or to shift right, what does that exactly mean? If I'm shifting right, am I multiply or divide? And if I multiply or divide, is meaning multiply by how much or divide by how much? Suppose that, okay, let's say that we would like actually to do or to understand how the shift operation works or what exactly is doing, but with the decimal number, Suppose that I have here number 2, decimal, correct? And this number 2, it is written as an example in 4 digits. This is 0002, correct? When you read that, you will just find that this is number 2. I'm telling you, please shift this 2 by 1 to the left. So the number will be 2, 0, 0, 0. So this will be the new number. How you read that number? 20. What is the relation between 2 and 20? It is multiplied by 10 to the power of 1, because it has been shifted left by 1, which means, by another sense, that shift left is multiplied by 10. Shift another one to the left, it will be 2, 0, 0, 0. How you read that number? It is 200, which again, how it is related to that? It is multiplied by 100. Or in another thing, say, shift left by 2 is multiplied by 2 to the power of the number of shifts. Why I said multiplied by 10 to the power of the shift? Multiplied by 10 to the power of the shift, because 10 is the base of that particular decimal number, correct? How many shifts is just whatever how many shifts. So when we shift left by 2, I multiplied by the base, which is 10 to the power of 2, which will be 100. And that's why this 2 becomes 100. The same appear if this is also 1 to the left, it will be by 3. So this means that it is multiplied by 10 to the power of 3, which is 2000. Apply the same exact rule if we would like to go the other way around by shift right. But it will be, instead of multiplication, it will be division. If you were to think about that example, 2000, and then shift 200, and then shift 20, and then shift 2, by the same thing. With the same exactly way, we can also think of a binary number. That if a binary number is here, 1, 0, 0, 0, and then again shift this, it will be 1, 0, 0. This is read like 1. How about this? Is read like 2. Why? Because it has been shifted by 1 to the left. So I have to multiply it by the base, which is 2, to the power of the number of shifts, which is 1. So I will multiply this one by 2 to the power of 1. How about if I will go another one, 0, 1, 0, 0, 1? How you will read this? It is 4. How it is related to that? It is multiplied by the base, which is 2, to the power of the shifts. So shifts is 2, so 2 to 2, 4. So it will be 1 multiplied by 4, and that's why this is 4. How about this? It will be multiplied by 2 to the power of 3, which is 8, and so on and so forth. You can think of this the same way also, the other way around. So shift left by 1 is multiplied by 2, or shift left by many will be multiplied by 2 to the power of the number of shifts. Shift right is division by 2 to the power of the number of shifts, and this is the same things as we mentioned, but all of these will be only on unsigned numbers. Because with the signed numbers, we need to think about a little bit differently, but with unsigned, this is the rule that we need to do. And that's why, by the way, we need a shift operation, because in some cases, it is a lot easier to do the multiplication by the power of 2 with this way than to implement a hardware multiplier. If you would like, just for your reference, to implement a multiplier, this will take a huge area in the FPGA. And we would like to reduce the area as much as we can. This is one of the things that a trick that we might use in order to substitute a multiplication operation with an easy hardware implementation side as just the shift. So with this shift example, suppose that we have shift left logic T2, S0, 8. How we will read that? This will be my destination, and this what I need to shift, and this is by how amount. What is the amount? So T2, this is the destination. We will have whatever in S0 shifted left by 8 bits, and then put the results here. Shift right for the same things, meaning that we will go to S0, shift right it by 8 bits, and then put the results in T2. Again, what is S0? What is T2? It's just the address of a certain particular registers. So let's say this will tell you, please go to register number 16. And then shift it by 8 bits, either left or right. and then put the results in that particular register, which supposed to be, as an example, a certain particular number. And that's all. Interestingly here, what I have forgot to highlight, that in that case with the shift, it just discard the first source and it deal with the second source. So this means that here will be just a 0. And it will just deal with the second source, which means this S0, it will be as a second source. So it will be written in RT as we can see here. So this is basically S0. And this will be the shift amount. And this will be the T2, which is the destination. And this is the RT, and this is the RS, which is 0 in that particular case. So you need to be familiar with that as well. So if I were to give you this and ask you to write it on that, you have to be familiar that you need to discard RS. This will just be 0, and the source has to be written in the second source in that particular example. So this AND operation, as we mentioned, you just take this, ended with this, put the results here. So in T2, address T2, this is an address, a drawer number. This is another drawer number. This is another drawer number. So you went to this drawer number, you found all of these data. You didn't know in advance what is there. What was there, you didn't know that in advance. You just went to the address. As soon as you went to the address, you have in hand all of the data inside. And then you went to that other address. And as soon as you went to that other address, you have hold of all of the numbers inside that particular register. And then you will do an AND operation. AND 0, AND 0. Then you put the results in that particular location. So it is 0. If you go 1 AND 1, it is 1. 1 AND 1, it is 1. 0 AND 1, it is 0, and so on and so forth. So now I know where to go and then where I should allocate my output. With the OR operation, again, this will be ORed with that. The results will be in T0. Again, we'll go to that register, and then we'll go to that register. And then I have holes now with the inputs in each of these registers, and I will do the OR operation. 0 or 0 is 0. 0 or 0 or 0. Take another 1 or 1 will be 1. 1 or 1 will be 1. 0 or 1 will be 1, and so on and so forth. And then will be the same things. Let's try to do a NOT operations. NOT operations, you can think of this in the assembly that just NOR and then T1, comma 0. Because A nor B, if you recall, it is not A or B. So I will get to do A or B and then not of them. But what is this 0? Interestingly, the MIPS guys have decided that the very first register number, the very first register, it will be a 0 register, meaning that it will hold a 0 value. And all of us will agree that we will refer to this as 0, Z-E-R-O. So, which means that when I write 0, I refer to register location 0, which has a 0. This is the only time that we will have things like that, that the address is referring also to the whatever inside, which is also 0. And all of this will be registers, because we will see later on that when I am dealing with numbers, if I would like to refer to a number, I will not basically use an R format, because R format, it will be only with locations inside my register. If I would like to refer to a number, this will jump us to another format, which we will talk in details a little bit later. Except the 0 number. 0, although it is still a number, but it is in the R format, since the MIPS guys have decided that the very first registers will hold a 0. And it would be helpful for situations like that. Suppose that I would like to do a NOT operation. NOT operation is not but ORing that particular number to a 0 and then invert. This will give you a NOT operation or invert operation. So if this is the case, to T1 here, it will just be inverted by this way. So 0 will be 1, 0 will be 1, 1 will be zeros, 1 will be 0, and so on and so forth. And this destination T0 will have just the NOT operation. So now we finished the R format. We need to switch the gear a little bit to another thing. So whatever we have covered till now is just dealt with the register. I'm telling the robot or the CPU from where you will get the numbers and where you will allocate it, and all of these inside one location, which is the register. I didn't give any instructions that will take anything from the memory to the register or vice versa. So I didn't touch the memory at all with all of my R format. R format is only dealt with one location. All of these 32 locations, from where you will get the information, from where you will allocate the information. But it's only in one location. It's just 32 places. But if I would like to take anything from the memory to the register or the other way around, I need to use a little bit of a different format, which we will cover. But also I need to use another also command in that particular situation. There are two commands that I usually or that I always use if I would like to move from the memory to the register or from the register to the memories. What are these commands? The first one is called load word, LW. And load word means that I would like to take something from the memory to the register. It's called load word. Why word? Because the memory, you can think of this that it will hold words, and I will take that word to take it from the memory to the register. But I have to say or to tell the robot two things. Where exactly the location in the memory and where exactly the location in the register. The same things as we did with the register. However, I'm just dealing now with two locations. Where inside the memory and where inside the register. But there is a trick on how to specify the address inside the memory. Let's say how we can do that. Load word from that location to that location. So this location is in the memory. This location is in the register. Store word, this is the other way around. I would like to store something from the register to the memory. So again, this is in the register. This is inside the memory. So the only commands that I will use to deal with the memory will be load word or store word. How I usually refer to an address inside the memory is by that. I will specify first a base address, and then I will specify the shift amount from that particular address. How much it is shifted from that particular address. Meaning that, for instance, I would like to tell you to go to a certain particular home address. But instead of telling you exactly the home address, suppose the home address is 200. But I would like you to go to 204. But I will not tell you explicitly 204. I will tell you 200, and then shift 4. So you will do 200 plus 4, then you know that you will go to 204. I can give you 400 and then shift 8. So it will be 400 plus 8, so you go to 408, and so on and so forth. And that's why it is usually written by that particular syntax. I'm giving you the base address, let's say the 200, and then I will give you the shift. So this gives us another way actually to represent a format, because now if you think about the 32 bits that I have, I don't have a shift amount. In that case, I might need to deal with a constants, because the 4 or the 8 in that particular example, the 4 and the 8, if you recall these particular examples, in the R format, there is no space to write any constants, any numbers. I'm just dealing with register locations. But in the I format, I need to do something like that. So I need to know two things, from where and to where. Yes. And that's why I need to have like two particular location addresses, RS and RT. And in some cases, one will work as the first source or the second source, or the other way around. We'll see like different of these things. You can think of this like one will be the destination, the other will be the source, or the other way around. I just need two addresses. The operand is still the same, because we mentioned at the very beginning that this operand will be constant with all the formats, which will tell me what is that format. And it might tell me also in other formats what's exactly that. Meaning with the operand, as soon as I will see a certain number, I will understand that this is load word. Or I may understand that this is store word. As soon as I will go to the table, it will tell me that this operand and the number associated with that particular command. But also I need a place that will hold a certain particular constant. This constant might be like a certain number, or it might refer to a certain particular address that I need to add. At the very end, I need a place to hold, or a location to hold that particular number. So they will just follow that 6 bits for the operand. They need, as we mentioned, like 2 places for addresses. So that's why they take 5 and 5. And then the rest is just for a constant. That's what this is, because we have again a 32-bit width inside the memory. And this might change if I give you another problem. Because again, inside the memory, I'm assuming that I can address a word, and this word is 32 bits. The width of a word is 32 bits. I might tell you later on in another example that the word, I will take it as 64 bits. It's not no longer 32, it is 64. So if it is 64, how you will change this kind of numbers? And so on and so forth. Then with this I format, it is referred to as immediate arithmetic format. With this address, it is 16 bits. So it can have anything from -2 to the power of 15 to the 2 to the power of 15 minus 1. With these 5 bits and 5 bits, we understood why it is 5 bits. This operand, it is also again 6 bits, as we have covered in the R format. So now I can understand, or I can implement a load word which has very first location from where I will bring the information inside the memory. I have the offset that I need to add, if you remember the 8 or 4. I have also a place to identify where I should allocate this particular address or data from the memory to the register. And I have an operand which will specify if this is a load word or a store word.